Alright, let's tackle another example. This time it is question 205. Let's read the question. Question 205. What is the direction and magnitude of the total force on the rectangular loop shown in the diagram? So what we are shown is one wire on the top with a current of 15 ampere. We have a rectangular loop over here with a current going through it of 30 ampere. We are asked what is the net force on this rectangular loop. Now note, we are given the dimension of this loop. We're told that the longer side is 0.3 meter. The shorter side is 0.1 meter. We are told that the distance between the first wire and the top of the rectangular loop is 7.5 centimeter or 0.075 meter. All right. We are not given the length of the top wire, but it does not matter because we are only interested in the force on that loop over here. All right. Now, what we need to do is first identify in which direction all of the force will be pointing. And note, every time you are changing the direction of one of the wire, we need to redo the computation. So basically, there will be 4 different force acting on this rectangular frame. I denoted them F1 for the left side, F2 for the top side, F3 for the right side, F4 for the bottom side. All right. Another point, we need to know in which direction the magnetic field will be pointing. This one is rather simple by now. We point our thumb toward the direction of the current, and the magnetic field on this loop over here will come from the current on the top wire over here. So this magnetic field over here, we point our thumb toward the current. The curl of our finger is the direction of the magnetic field. If we look, that means for anything below the wire, the magnetic field will be pointing into the board. All right, so magnetic field into the board, that's important to distinguish in which direction the force will be pointing. Now note, in order to solve the magnitude, we will need to be using 2 formulas. The formula for the force on a current carrying wire, it's equal to the current of the current carrying wire. So in this case, it will be 30 amp. This is the one we're considering. Multiplied by the length. Well, that depends on which side we are considering. They are not all the same. Multiplied by the magnetic field. The magnetic field will be from this wire over here. And the magnetic field can be calculated using the Biot-Savart law over here. Now, note an important point. At the last section of last chapter, we said that a uniform magnetic field will create a net force of 0 on a closed loop. This is still true. The thing here is the rectangular frame is not in the uniform magnetic field because the magnetic field is coming from this wire and the magnetic field strength is dependent on the distance from the wire. In other words, the force on the top side and the bottom side of the frame will not be the same. All right, let's have a look at the direction of our force. We're going to be starting with F1. So basically we see the current is going in that direction counterclockwise. So from the point of view of F1, the current is pointing down, the magnetic field is pointing in, so I curl my finger toward, and my thumb is pointing to the right. So as always, I draw a vector diagram. I got F1 pointing to the right. Then we look at F2. In this case, point toward the current. The finger curl inward toward the magnetic field. My thumb is pointing down, so F2 is pointing down. We follow the same logic for F3 and F4. We got F3 pointing to the left, F4 pointing up. Now, there's something interesting here is that if we look at F2 and F3, at all point, they share the same distance from the current carrying wire on the top, which is responsible for the magnetic field. What that means is they will share exactly the same magnitude. F1 and F3 will be the same magnitude, but they point in opposite direction, which means they will cancel out. Okay, so there's a decent chance that you get a question similar to that one in the final at this point. All right, you can use that trick to eliminate the calculation for F1 and F3. If you wanted to calculate the magnetic field, the magnetic force, on F1 and F3, you will need to integrate. Basically, you will need to integrate each of the small piece of the wire and add the magnetic force on all of the part, all right? We are not going to cover this in my course, but maybe that will be a bonus question at the end. We see Maybe someone will be able to solve that one. All right, so we came to the conclusion that F1 is equal to minus F3. Now let's calculate the magnitude of F2 and F3. Note, because these values are set, so when we look at the magnetic field, we got permeability of free space, current 2 pi, only the radius is not set, so I input the value just to get a sense. We get 3 multiplied by 10 power minus 6 divided by the radius. It will be simpler to manipulate these variables here. Now, know that I over here is the current of the top one again, okay? That's a common mistake. Let's look at the force. We got current, and now this current on the force is the current in the frame, the length, depending on which side we're considering, and the magnetic field, which is this formula. Okay, so on F2, we got 30 amp. We got a length, it's F2, so it's 0.3 meter. Note F4 will also be 0.3 meter. And multiply by the top part of the magnetic field divided by the radius. Now for F2, the radius is this value, 0.075 meter. We input the value, we get 0.00036 Newton. Note, I added a minus just to remind myself that it is pointing down. Okay, that's important. We repeat the same step for F4, and I'm not sure if you can see. Yes, anyway, I'm gonna erase everything and restart in a moment. All right, so actually, we really do need to see the bottom part. Okay, sorry about that. So basically, the top number are the same for F4. The only difference now is that it's the distance from the current carrying wire on the top. And we got 7.5 centimeter here, 1 centimeter here, 10 centimeter here. We need to add them up. What that means is 0.075 plus 0.1 is the radius. I did not calculate this value yet. We need to do it. At this point, we got magnitude, we got direction. I don't need the top part. I just need to compute this value. I need this value, the direction, perfect. So if you need to pause the video, do it now. I'm gonna erase from this part up. All right, so let's calculate. All right, so I get F4 is equal to 1.54 multiplied by 10 minus 4, or 0.000154. All right, if we look, F2 is pointing down, F4 is pointing out, so net force will be in the y direction. So it's equal to Fy, it's equal to F4 minus F2, which is equal to 0.000154 minus 0.00036, and we get a net force of minus 0.000206 Newton. So minus, which means that the resultant force is pointing downward, which means that the frame will be repulsed from the top current carrying wire. Okay, so this is our answer. And like I mentioned, you will definitely get a question using these concepts in the test. So if there's anything unclear, let me know. These questions, especially how to identify which current is which magnetic field is which, is a common mistake. Do not wait. These are more complicated questions, I know, but you will have plenty of time to practice this before the final. Make sure you do not waste your time though. All right, we're going to be solving one more example regarding the force on two parallel current carrying wire, and we are almost done with this chapter now. Okay, see you in the next video.